Now, let's talk about chirality. And chirality is kind of a messy subject because what we teach in organic chemistry is an oversimplification of what chirality really is. So for a molecule to be chiral, it has to lack an inversion center. Now, the problem with that definition is that even in organic chemists, as much as they boast that's the correct definition, really struggle to see inversion centers. So more what we mean when we say a chiral compound is something that it has a mirror image that doesn't superimpose over its original self. So the famous example, you'll see this in my notes, you'll see this in every book, is your hands. So if I take my left hand and I take a mirror image if I get my right hand, but there's nothing I can do with my right hand to turn it or fold it or rearrange it in such a way I can recover my left hand. So this is chirality. When we introduce an atom to a molecule which generates a mirror image that cannot be superimposed over the old image, this is a chiral compound. And chiral compounds have chiral centers. These are the atoms that make them chiral. And a molecule can have multiple chiral centers. So how do we identify the chiral center? Well, the big thing about a chiral center is that this is going to focus on our tetrahedral carbons. So when we're looking at organic compounds and trying to identify who's chiral, where there's chiral, we're going to focus on the sp3 hybridized carbons. Now, to be a chiral center, if we look at the carbon atom, it has to have 4 unique groups connected to it. So if I look at this drawing here, I have a hydroxide, an OH group, an alcohol, a bromine, and I've got 2, 3, 4, 5, 6, a hexene chain. Certain carbons in this compound are chiral, certain carbons are not. So let's start with this carbon here. So if I draw that carbon, above it I've got 1, 2, 3 carbons in an OH group, and beneath it I've got 2 carbons in a bromine group, and connected to this carbon are 2 hydrogens. Now, here I don't have 4 unique groups on this hydrogen because 2 of the groups connected to this particular carbon are hydrogen. So we would say that this carbon is achiral. It is not a chiral carbon, it is achiral and doesn't contribute to any chirality of the molecule. Compare this to something like the bromine. So if I look at this bromine, this carbon has a bromine, hydrogen, a CH3 group, and a 1, 2, 3, 4 group that looks like this. So around this carbon, I have 4 unique chains. I have the CH3, hydrogen, Br, and this group coming off with the alcohol hanging onto it. So in this case, this would be a chiral center. If we look at the OH group, it's a similar story. I've got my carbon with an OH, hydrogen, above it I've got a CH3 group, and beneath it I've got 1, 2, 3, 4. A chain hanging out. So what I see are 4 unique groups centered around this carbon. So both the carbon connected to the bromine and carbon connected to the hydroxide here are chiral centers. So there are 2 chiral centers on this molecule. So when I have a chiral center, it begins to matter whether or not I use the wedge dash because I'm going to take a mirror image. So in the case of my hand, it really matters the order whether I go left or right from my pinky to my thumb or my thumb to my pinky. Same thing is going to be true on this. If we have wedges or dashes, it's going to really dictate what they are actually, how they're actually arranged with each other with regard to space. So how do we identify which chirality we have? How do we even identify chiral centers? We're going to talk about in the next video when we look at how to translate this to a Fisher projection.